Radioactivity is actually talking about the decaying effect of an atom. So we have this atom, so protons and neutrons, we have this. So what happens, neutrons, let me draw them. So what happens, oftentimes it is seen that something happens at the nucleus, and this is random. Randomly we have radiations coming off. Now these are not like any other radiation, these are specific radiations. They break down and radiations come off. Now the radiations that we have is the alpha particle radiation, which is, we have from here 2 protons and 2 neutrons. Let me use green color. 2 protons and 2 neutrons just come off, they're spitted out. So these are the alpha radiations, alpha particles. This is one type of radiation. 2 protons, 2 neutrons, just spit it out. And if you remember, it is written like 2 proton here, and proton plus neutron, atomic number is 2, mass number is 4, and this is similar to a helium nucleus. Of course the electrons they are missing, they are not electrons, so it is going to be positively charged. The charge is going to be plus 2. If it was a helium atom, it is going to be plus 2 and minus 2, they are going to cancel off. So the first type of particle radiation is alpha particle radiation. Now the next one that we have is, think of a proton. So we have, think of a neutron first of all. So if you have a neutron, let me use neutron as a neutral color. This is neutron. So this neutron is breaking down into a proton. Let me use purple color for proton. Breaking down into a proton and an electron and an electron. This electron, which is negatively charged, is the beta particle. So basically a beta particle is nothing but an electron, and it is written like this. The symbol for electron is E. It does not have any protons, so it's -1, and the total number of mass number of proton and neutron is 0. So this is how a beta particle is represented. And now the final type of radiation, that's a gamma radiation. We don't call it a particle, it's a transverse wave, so we call it a gamma radiation. It's an electromagnetic wave. Now the most ionizing is alpha particle, most ionizing. It means it is very reactive. The least ionizing is gamma particle, and beta particle is in the middle. The most penetrative is gamma particle. It travels infinitely. No one can stop it. Infinitely. Beta particle is stopped by aluminium foil, very few centimeters of aluminium foil, and alpha particles are stopped by a piece of paper, very easy to stop it. Alpha particle can travel around 5 to 8 centimeter. Beta particle can travel around hundred centimeter. So this is the basic idea. Now alpha particle are the most ionizing, so that means since it doesn't travel that far, so if you're a bit far away, they will disappear, they will ionize with whatever they can get, the air or something. But if they can come in contact with the skin, there can be mutation, there can be some skin cancer. So that's why alpha particles are in that terms most dangerous. Now referring to the equations, how do we talk about the equation? An equation is written like you have to balance an equation. So let me break it down into two types of equation. One is alpha and the other is beta. So let's use this. So this is equations. We have to balance the equations. Now the first is for alpha particles. Now if you think about the equations, let me give you an example. The first one is we have this decay going on. This material, it has 222 nucleon number, meaning mass number, and 88 protons. Now if we balance the equation for an alpha decay, alpha particle, this is breaking down and 2 proton and 2 neutrons is coming out. So what we have here is 218 and 86. Now why is this happening? Because in alpha particles it is 4 mass number and 2 proton number, 2 proton and 2 neutron, that makes it 4. So if you balance it, you will see that 218 plus 4 is 222 and 86 plus 2 is 88. So they have to balance each other out, so they have to match. So if I give you a question like that, how to balance an equation like that, you can see, suppose this is the question, 234 mass number and 92 proton number. Now this is unknown, this is unknown, and we know this is an alpha decay. So 4, 2, it's a helium. So how can we balance it? It's very easy. So this is 234 on one side. So this 2 neutron and proton together, mass number, and this has to add up to 234. So this would be 230. And we have 92 protons here. So this is 2 protons. So this and this 2 has to add up to 92. So this will be 90. So that's it. Let's do another example. We have 216 mass number and this is unknown. It balances to, the mass number here is unknown, this is 82 and this is an alpha particle. So how do you balance this? First of all, the proton number, there are 82 protons here and 2 protons here, so total is 84. This has to be 84. So this is 84. So this is 216 here, this is 4, so this is going to be 212. So it is balanced. So this is how it works. Now let's talk about beta decay. So beta particles. One thing is very important to remember when we talk about beta particles are actually coming from a neutron is breaking down into a proton and an electron, and the symbol of electron is -1, meaning negative. So in order to balance it, this is what happens all the time. We have, suppose this is the mass number, this is the symbol for the element, and this is the proton number. And if it's a beta decay, if the beta particles are coming out of the nucleus, so what's going to happen? The mass number will always be the same, because the proton is replaced by the neutron is replaced by a proton. So the total mass number is proton plus neutron, so one goes out and another comes in, so the mass number will be the same. What would happen here? The proton will increase because the neutron is breaking down into a proton, so the proton will be increased by 1, and in order to balance it, we have this beta particle which is -1, so z plus 1 minus 1 is ultimately going to be z, so it is balanced, and A will remain the same because A plus 0 is A. So this is how it is working. So let's see an example. So we can use this for beta decay. Suppose it has 137 mass number and 55 proton number, so it balances to 137. It is going to be the same, and it is going to be one more. The proton number is going to increase by 1 because the neutron breaks down into a proton, so it would be 56, and the beta particle is like this. So 56 minus 1 is 55, and 137 plus 0 is 137. So this is how it is working. So let's do a couple of more examples. So if we have here 234 and we have here 90, so this is unknown and this is unknown, plus we have a beta particle. Now you know this mass number will be unchanged because the neutron is replaced by a proton, and mass number means proton and neutron total, so nothing is decreasing, is the same. So this will be 234, so it balances. 234 plus 0 is 234. Now 90, a proton will be added. In a beta particle, proton increases by 1, so this would be 91, and it is minus 1, so 90 minus 91 minus 1 is 90, so this is balanced. So this is how it works. Now another example can be, so this one and this one for beta decay balancing the equation, and these are the alpha decay balancing the equation. Let's talk about half-life. Half-life is a very simple concept. It is the time taken for half of the mass to decay. So for that, the concept of radioactivity has to clarified again. Now first of all, when we talk about radioactivity, these things are called actually activity, and the unit of this is called becquerel, BQ, becquerel. So becquerel is the unit of activity, the amount of particles that are coming out, and there is a counter machine that can count this activity called Geiger-Müller counter, GM counter. So what happens, GM counters counts the activity, meaning the radiation that is going on. So one thing is that if there is no radioactive particle present, GM counter will still give some radiation because there is something called background radiation that always goes on. Now background radiation are radiation that is coming from the sky, it's called cosmic rays, and also from the ground of the earth, called ground and building radiation. So cosmic rays and ground and building radiation are the primary source of background radiation. So if you turn on the GM counter, you will see there is some activity going on, 500, 600, so that's the background radiation. Now if you bring a radioactive material close to it, that background radiation will increase, suppose 700. So if you know the background radiation, if you know the present radiation, if you subtract it, you'll get the activity, what is going on. So activity is measured by becquerel, and one important concept is the concept of half-life. Half-life is the time taken for the mass of a radioactive particle to decrease by half. That time is called half-life, and this is best clarified by an exponential graph, which is this. So this is the activity and this is the time. So this is what the graph looks like. So suppose the activity at the beginning is 100. So half-life would be, for that activity from going down from 100 to 50, the time that it takes. So this time would be the half-life. So the time taken for half of the mass to decay, so the time taken from the activity to become half of what the activity was previously there. So from this the half-life can be calculated. So let's see an example of half-life. Now suppose we have an activity of 24 becquerel and the half-life of the activity is 100 years. So in 100 years it would become half. So the question is, how long will it take for the activity to reach 6 becquerel? So this is how it should be done. Half of 24 becquerel is 12 becquerel. So it will take 100 years. Half of 12 becquerel is 6 becquerel. It will take another 100 years. So it will take a total of 200 years for 24 becquerel to come down to 6 becquerel. Let's do another example. When we talk about, suppose if something has 200 becquerel and you want to know half-life is 20 becquerel, so for that 200 becquerel, if this is 200 becquerel and the half-life is 20 minutes, so for this to become 100 it would take 20 minutes. For this to become 50 it would take another 20 minutes. For this to become 25 it will take another 20 minutes. So this is how it goes on.